La soutenance de thèse donc, de doctorat en physique d'Aurélien DELPHIN concernant l'IRM et les développements de l'IRM en fingerprint, en anglais comme en français, sur l'oxygénation et cartographie d'oxygénation cérébrale. Et c'est un plaisir de partager ce jury avec des éminents spécialistes que j'introduirai au fur et à mesure avec les deux rapporteurs, qui sont le professeur Van Hosch de Leiden et Jacques Fellinger qui est en ligne, qui s'excuse et qui est à Nancy, qui est BPH pour l'université de sciences économiques, donc à Nancy. Aurélien, on t'écoute et puis après, on fait le tour de ton nombreux jury.
Merci. Je vais passer en anglais. So, thank you everyone for being here today. I'm quite touched by your presence. I'm very proud and excited to be in front of you, in front of this wonderful jury, to present my thesis titled Developments of MR Fingerprinting to Map Brain Oxygenation. I was supervised here by Emmanuel and Sommer. And when you look at the title, I believe two questions arise. Why do we want to map brain oxygenation? And what is MR fingerprinting, and why do we believe that MR fingerprinting is a good way of doing so? And I'll try to answer those questions before we get going any deeper in the subject. I believe you all know that oxygen is essential for the body function and then for the brain function. Oxygen enters the body through the lungs. It is captured by hemoglobin in the blood, which becomes oxyhemoglobin, carried by the arteries towards the organs where it is consumed, which creates deoxyhemoglobin, which does not carry oxygen. And that is carried in the veins through the heart and the lungs in a continuous circle. And the important thing here is that oxy and deoxyhemoglobin do not share the same magnetic properties. A bit more on that later. Just a bit of semantics. Oxygen and brain oxygenations are kind of confusing notions. So if I do not specify otherwise, when I say oxygenation, I mean oxygenation saturation, SO2, which is the ratio of the amount of oxyhemoglobin over the total amount of hemoglobin in a region of interest. And I'm also going to meet the oxygen extraction fraction notion, which is the variation of the SO2 between arteries and veins in a region of interest. With that behind us, the brain represents 20% of the human body O2 consumption, which is a lot because it only represents 2% of the mass. So oxygen really needs a lot. The brain really needs a lot of oxygen. And unfortunately, some brain pathologies are known to be associated with impaired blood flow, which are, of course, consequences on brain oxygenation and on brain function. So we are talking about brain tumors, traumatic brain injuries, strokes, and others. And in the case of stroke, one clinically relevant question is to delineate the ischemic penumbra, which is the region of the brain where the function is lost but could be recovered if the blood flow was restored. The best way of identifying the ischemic penumbra will be to use oxygen 15 PET scans so far. It's the best way that we have to measure the OEF. Here you can see in green an increase of OEF that is penumbra. But PET measurements of that kind are poorly available and not compatible with an acute care context. So we have to find surrogates. Here is an example with MRI. It is absolutely not a measurement of oxygenation. It's really just a surrogate. We do perfusion and diffusion images, and we compare, we look at the mismatch between the anomalies that can be seen on these images. Here you can see on the perfusion image, delineated in red, the mismatch between the two images, and it matches quite well with the penumbra that is detected by PET scan. So that could be a good surrogate. But it's not always the case. Here, the MRI surrogate finds a penumbra where there is actually no, as confirmed by the PET scan. So a new cerebral oxygenation mapping technique is needed because delineating the penumbra is actually what will guide the therapy. And so there is a very high need for a proper identification of this kind of issue. And as I discussed in the manuscript, There is no real candidates to do that in the literature so far, and nothing is really compatible with acute care. Maybe that the best chance that we have to be to exploit the blood oxygen level dependence or bold sensitivity of MRI. But again, there's no current way of doing that in acute care. And we propose to try and do it using magnetic resonance fingerprinting, or MRF, which was introduced in 2013. To perform MR fingerprinting, you need 4 things. The first one is a dedicated MR sequence, which is a list of instructions that you give to your MR scanner to tell it how it should acquire images. You need to acquire images, and we actually acquire quite a lot of them. And to keep the exam time short, we acquire degraded images. So you can see here a human brain. So this image has no real relevance as it is, but if you look at one region of the brain, what we call a voxel, which is the 3D version of a pixel, and that you look at one voxel across all the images that you make, you can build this kind of temporal evolution that we call a fingerprint. And the shape of this fingerprint is entirely determined by the sequence that was used during acquisition and the properties of the tissues inside the voxel. In parallel to those acquisitions, you have to generate a dictionary, which is a database of tissue properties that you expect to find in your subjects, and their associated simulated fingerprints. So you simulate the shape of the signal that you would have from a voxel having those properties, and you do that a few 100,000 times, million times, and you obtain a dictionary. I want to stress here again that the shape of the signal changes just due to the change of the parameters. And once you have all that, you need to perform the reconstruction step. So you need to build the maps of the parameters that you are interested in. And you do that, the most classical way of doing that is doing matching. So you take your acquisition here in blue and you compare it one by one with all the entries in the dictionary, which is done here. Maybe you can see that this is the case where the simulation looks the most like the acquisition. And so the train of thought is to say, this voxel in my subject gave this fingerprint, which looks like this simulation, which comes from those voxel parameters. So this voxel has those parameters. You repeat that for the whole brain, and you are able to build, just like that, 3 parametric maps. So MR fingerprinting is fast. It takes about 3 minutes to obtain this kind of results, and it will take more than 20 minutes with classical MRI. It is intrinsically multiparametric because you build as many maps as you have parameters in the dictionary. And it opens many new possibilities of new sequences that can be used and new parameters that can be that you can map. Because as long as a sequence is sensitive to a parameter and that you can include it in your simulation method, then you are able to make maps of that parameter. And that's exactly what we propose to do for the oxygenation. The method was coined MR vascular fingerprinting in 2014 by Sommer. And the idea is exactly the same. You have a sequence, you acquire fingerprints, you simulate a dictionary, so you've got some parameters that you expect, and they are associated with vascular geometry, because we are looking at vascular properties, especially with oxygenation. You build a dictionary, and then you can reconstruct maps of the parameters of interest, which are for us the blood volume fraction, which is the amount of blood in a region of the brain, the mean radius of the vessels in a region of the brain, and most importantly, the SO2. So here is an actual map of SO2. The method was found to be working well, but has some issues. It requires an iron-based contrast agent, which is not compatible with clinical care. Actually, the way we do it is that we do not acquire directly with fingerprints. We acquire first signal before injection of the contrast agent, one signal after, and we take the ratio post over pre to build our fingerprint. That is not compatible with clinical care. We have, of course, a non-realistic vascular network representation. The brain is not in 2 dimensions, and we have vessels that have much more complicated shapes. And this is expected to decrease the sensitivity of the method. And the sequence that we use is not optimized for MRvF. It's a sequence that was designed for more classical MRI. We've been using it, but we know that we can find better sequences that would allow us to have a better sensitivity and to get rid of the contrastation. That will be the ground objective of this project, to design an MRvF protocol with increased sensitivity to SO2 and without needing any contrast agents. And the concrete steps that we are going to take towards this objective are to improve the simulation realism and performance, to be able to perform state-of-the-art MRF acquisitions, because it's not something that you can do out of the blue like that. It requires development. And we are going to explore new sequence types to try and gain more sensitivity and get rid of the contrastation. That will be the outline of my presentation. I'm going to present the tools I've been developing to be able to perform MRvF experiments. And then I'll show two studies I've been conducting. The first one being on the impact of using more realistic vascular representations in the dictionary generation step. And the second study is about finding new sequences with more sensitivity and low contrastation. We can dive right into it with the work I've been doing on the simulation parts of the project. Here is a small outline of what you need to perform MRF experiments. And so the part I'm going to present is focused on simulations here. I've been getting knowledge on MR simulations by studying MR theory, implementing the Bloch and EPG simulation tools that are quite classical, and doing some cross-validations with them. And I've also been working with reworking a tool called DCEC that was developed in the lab into something that we call now MRVox. I'm going to present. So there were quite a lot of adjustments to make this tool suitable for MRF and MRvF especially. I've been working also on geometry generation, some performance issues, and some validations. I'm going to present that here. In its current state, the MRVox tool works like that. You give it a parameter file that describes all the voxels that you want to include in your dictionary before parameters of interest that you want, and you give it a file that describes the sequence that is to be used. MRVox takes that, makes some computation, just a few, and gives you the dictionary in the end. And actually, what happens is that MRVox generates a vascular geometry, here represented in 2D with the blood vessels and the tissue. And the presence of deoxyhemoglobin in the blood vessels will create magnetic field inhomogeneities that are represented here in yellow and blue. And those inhomogeneities are the only thing that we can be sensitive to that will give us information to the vascular content of the voxel. So this is, we want to be sensitive to those kind of things that MRVox computes. And so MRVox computes magnetic field inhomogeneities. It also computes the magnetization at all points and all time in the voxel, which is quite time consuming. It includes diffusion effects. We have quite a lot of flexibility of the sequences that we can use. And in the end, we obtain a complex signal. And here it's just a 2D shot, but we have 3D representation of the magnetization vectors processing in the voxel, which is quite interesting to look at when we consider MR theory. It's been a nice tool to use. We also developed a 3D version of MRVox by implementing 3D vascular networks like that are straight cylinders, and we added the possibility to vary the oxygenation level between the different vessels that we generate to mimic arteries and veins and capillaries. And with this tool, we started doing some validations against literature, cross-validated MRVox against Bloch and EPG simulations in plain voxels, which is cases that the free tools can all simulate. And we studied the influence of the presence of vascular structures inside our voxel and how it impacted the signals by comparing MRVox to some models that were listed in this review here by Dixon. So basically what we do is that we assess how much the signal changes during spin echo and gradient echo experiments against some models from the literature that are dashed for spin echo and solid lines for the gradient echo. You can see that the models do not really match with each other. It's because they all make different kinds of assumptions about the diffusion, about the representation of the vessels, and so they do not match with each other. And you can see in black how MRvF fits into this. It follows the general trends of all the models, and given the differences between the models and with MRvF, we believe that our tool is sufficiently precise, accurate, and realistic to allow us to perform the kind of experiments that we want. So we kept the tool in this state so far. And this 3D version also allows us to not only use straight cylinders as vascular representations, but also to include some realistic brain networks that were imaged here by Thomas Christen and Raphael Saruk with 2-photon microscopy. And using that in MRvF gives magnetic fields in homogeneities that are more complex than what we have with just cylinders, and that's expected to provide better results for vascular fingerprinting, which will be the focus of study 1. So we'll see about that a bit later. MRvF is then a tool that was developed from something we had in the lab, but it was completely renewed for MRvF purposes. I used it extensively on several machines here. We are quite confident that it runs the way it should, and it is a tool that is one of its kind as far as we know, and so we've been sharing it with Dr. Audrey Fan in UC Davis and Professor Vanush from Leiden University, who is in the jury today. And that concludes this part on the simulation work I wanted to present. I'm going to continue and present the work I did towards doing MRF type acquisitions. So here we are in the MRF pipeline. And I've been working a lot with preclinical acquisitions on our Bruker devices here on the Earmarsh platform. I studied how to develop modules for Bruker. I continued the development of a module that was already started by a former student. I validated the results against some phantoms experiments and on some live animals, and I also validated parts of the physics that happens in the MRI scanner. And I've been working more recently with a clinical tool that we obtained through a collaboration with Philips Research that we use on our free Tesla scanner for clinical research. It's an MRF module that is developed by a team led by Maria Bonilla, who is also in the jury today. So we've been using this module on phantoms and volunteers. We compared the results that we obtained with standard axiometric sequences, and we started implementing some custom MRF sequences. And I'm going to present that to you. So we obtained the module and we tried it on some objects, and at first on a beach boot, which was both healthy and volunteer. Here is the kind of results that we obtained. We have very degraded images as expected. We have degraded signal evolutions as expected, but the module on its own with its own dictionary and reconstruction method is able to reconstruct very nice quality maps of T1, T2, and proton density, which are classical properties that we quantify in MRI. So the module works great on its own, and it's very easy to use, and we have great flexibility and kind of sequences that we can use with this module. So we tried that by implementing some sequences from the literature. So here are examples on my brain, actually, which is very nice. And so we've got sequences from Jiang that were published in 2015 and from Gomez from 2019. We obtained, so those are acquired signals and simulations that were batch simulations that we performed with our Bloch tool. Here are reconstructed maps, which are of good quality despite the low resolution that we use here, and the differences that you might see if your eye is trained between those maps are actually expected from the literature. So we are quite happy with the fact that we can use basically any kind of sequence that we want in this tool. And it has been very great to use. We intend to keep using it in the future. As I present, we learned a lot about how to do some imaging on humans, which is not the same as doing imaging on rats and mice. We learned a lot how to properly tune all the parameters in the module to be sure that we acquire exactly what we want to acquire. And we will keep working with this module, of course. It is worth noting that we waited 1 year for the authorization to collect the data from across the street on the hospital computers and bring it here in my office. We got the permission on Thursday, big win for us. And this has been kind of delayed in our experiments on this thing. That concludes the parts on acquisitions that I present today, and I'm going to conclude this tool development section with the developments I made for reconstructions. So we are here at the end of the pipeline. We've got acquisitions, we've got simulations. We need to combine them to obtain the maps that of interest that we want. So I started during the thesis by developing my own interacting reconstruction tool with a graphical interface to see how well the acquisitions were matching the simulations, and it has been great to debug both the simulations and the preclinical modules that we have. And more recently, I've been working on the MP3 project from Dr. Bolsa, who's in the room today. So, which is a reconstruction tool developed in the lab and shared open source with the community. I participated in developing MP3. I built a general MRF module from an existing one that was very targeted towards just hit sequences that was developed by a former student. I solved some run issues with this module, and I developed a data viewing solution that I'm going to present. MP3 is quite a powerful tool. It's an image processor written in MATLAB and that relies on SPM. It also relies a lot on a data converter by Aurélien DELPHIN in the team. And it includes, in particular, among many other things, some modules to reconstruct MRF parametric maps with either classical matching, as I presented before, or by implementing a machine learning tool, which is a GLIM implementation dedicated for MRvF from the thesis of Fabian in the team. The idea is to learn the relation between the signals and the parameters in the simulations, and then when we show the algorithm the signals that we acquire, it directly gives the parameters that are associated. I'll present that just a bit later. Here is a graphical example of what you can do with with MP3. Sorry. You can display up to 4 maps, which can be the reconstructed maps that you reconstruct, or the actual acquisition that you make and the matched volume that you obtain from a matching reconstruction. So you can look at your maps, which are all registered on the same space. It's very friendly to use. And we can assess here again how well the acquisitions here in green compare with the matched signals in blue. And seeing 4 maps is already nice, but the specificity of MR Fingerprinting is that with one acquisition, you generate 3, 4, 5, 6 different parametric maps. And if you do that in several subjects, it gets quite hard to keep track of all the images that you made and where the process worked or not. And so to assess that, I developed an HTML viewer. So MP3 creates an HTML page that you can see on your web browser with all the interactivity that you can have there. And you can see all your subjects and all your metrics, the different metrics that you have, and that is very convenient to assess on which subject the acquisition may be failed, or on which metric, which dictionary that you use, and the kind of thing that you want to try, which one didn't work. And I should specify maybe that those are rat brains. Maybe not everyone is used to saying rat brains. So this is actually a rat brain. In conclusion, on these two development parts, we now have everything that we need to perform MRvF experiments, which was not the case at the beginning of this thesis. We've got a way of doing acquisitions on animals and on humans. We've got a way of doing simulations dedicated for MRvF. And we have several ways of reconstructing the parametric maps that we want. I'd like to stress out here that we've been collaborating and sharing a lot throughout these projects. Our simulation tool is shared with UC and LUNC. We are in collaboration with Philips Research for our clinical acquisitions, and the MP3 tool was published and shared open source with the community. So with all that, we can actually start to try and improve MRvF, which was the objective of the project. The first study I did towards improving MRvF was to use realistic 3D vascular networks So we are working here on the simulation side of MRF. And the idea is to evaluate the impact of the realism of the vascular representation that we use on the estimates that we get. The 2D model of the vascular structure that I showed before is too simplistic, and we know that we lose some sensibility here. Is the 3D model with straight cylinders that I showed before as well sufficient, or do we need to go through the process of obtaining actual vascular networks from imaging, for example, microscopic imaging? Do we need to do that to have proper MRvF estimates? To assess that, I've been generating 3 dictionaries. The first one is called 3D Micro. It is based on actual vascular microscopies. I'm going to show you how it looks in 1 minute. So we got vascular microscopy data sets from the nets that are publicly available. We process them to obtain MR-sized voxels to perform our simulations with the help of an MG student that is supervising. We perform some erosion steps to obtain continuous BVF and R distributions, so blood volume fraction and radius distributions, as is expected to be found in tissues. And we generated a dictionary with that, and we did also a 3D and a 2D synthetic dictionary with straight cylinders, using the BVF and R distributions that come from those voxels that we got from microscopy data sets. Each voxel is attributed a single SO2 value, so all the blood in the voxel has the same SO2. There's no difference between arteries and veins so far. SO2 is distributed along a sawball sequence, and same goes for T2 in the voxels. To illustrate that, here is what it looks like. We segmented 28,000 voxels of this kind, and we intend to use that to generate the dictionary. This will be the vascular representation inside our dictionary. And we wonder if doing all of that provides better estimates than using this kind of simulated vascular representation, or just the 2D representation that we had in the original MRvF implementation. To assess that, I used some retrospective animal data that were acquired by Dr. Lemasson here in the lab a few years ago. I used 17 animals, 8 healthy rats and 9 rats implanted with 9L tumors. The sequence used was as presented in the first paper of MRvF, adjusted sequence with and without contrast agents. The fingerprint that we use is not the ratio post over pre here, it's the concatenation pre and posts, and I'll explain that later in this presentation. And the very interesting thing with those data is that, so we want to assess if we've got good estimates in vascular parameters with fingerprinting, and especially good oxygenation estimates. And we also have a second measurement of the local tissue oxygenation concentration, which was acquired in the brain of those very animals that were in the MRI with an intracranial fiber. And so that will serve as a ground truth on how much oxygen there is in the tissue from which we are going to get images. All processing was, of course, performed on MP3. I reconstructed maps with matching and learning, which we call here dictionary-based matching and dictionary-based learning. And we also reconstructed some the maps of the parameters of interest through analytical models that require more acquisitions than just the just-fit sequence, and that were used before MRF was around. Here is an illustration of how the learning reconstruction versus the matching reconstruction impacts the quality of the images. Here on the bottom line are the results from the matching. Those maps are actually already of very good quality, considering that we have only 28,000 voxels. We've got very nice maps, but if you look at the learning obtained maps, you can see that they are smoother, and actually they are not smoother, they are less noisy. And ultimately, we want to be looking at images for clinical values, so we decided that we were going to keep using throughout this study the learning tool, because it provided maps of a better quality. Here, is an illustration of the results from the different dictionary that I presented. So here we've got the results with the learning reconstruction of the 3D micro dictionary, 2D synthetic, 3D synthetic, and the analytical models that were used. And briefly, we've got here in healthy tissue, the values are very comparable between the different reconstructions, and we've got a clear increase of the blood volume fraction in the tumor. Same goes for the radius, quite comparable values in the healthy tissue and increase in the tumor. Same goes again for T2. And on the SO2, we cannot conclude that easily. First, in the healthy tissue, the 3D micro dictionary provides lower estimates than those from the other reconstructions, and those are actually more in line with what we expect from the literature. And more problematic, we've got a clear increase of the SO2 here, a decrease here. Kind of hard to say what happens with the 3D synthetic dictionary, and here as well with the analytical reconstruction. So we performed some group analysis, and the conclusions are the same as what I presented. And again, for the SO2, we've got a statistical increase of SO2 for the 3D micro dictionary, statistical decrease for the 2D synthetic dictionary, no statistical change for the 3D synthetic dictionary, and an increase with the analytic method. So how do we decide which dictionary provides the right values? Well, we have, if you remember, we have PO2 measurements from inside the brains of those very animals, and here are the findings from that. So we've been, well, they have been, I did not take part in those experiments. They have been imaging, acquiring the PO2 in both healthy and tumoral hemisphere at 2 different depths and on repeated measurements. And on the average results, we have a statistical increase of the PO2 in all the animals, which is linked with an increase of the SO2. And on one animal, I wanted to show you what the stability of the results. In this animal, we've got both depth, a statistical increase of the PO2. And so we conclude that only our 3D micro dictionary finds the right oxygenation trend in the tumor, which is confirmed by this PO2 measurement. So we showed the interest of using 3D realistic vascular networks for MRvF. We showed that it is beneficial to do so, which was not found by a previous study by Puvio, but they had only 6 voxels from microscopy. They were doing lots of transformations on them, but they did not. They concluded that it was not a beneficial thing to do. We've got estimates in healthy tissue that are in line with the literature, and we've got SO2 trends that are actually confirmed by in situ measurements. So we believe that we clearly show the interest of using this kind of realistic vascular network. And we also I also want to say here that we can work with that few signal, 28,000 signal in the dictionary is not a lot for standards of MR fingerprinting. And with our machine learning algorithm, we still obtain very good quality notes. I have some, I've been presenting those results at ISMRM 2022. And I've got some new results from 3 weeks ago that I want to present that I submitted for ISMRM 2023. It's human data acquired at Stanford at Free Tesla with just its sequence with and without contrast agent injection, which they can do because it's Stanford, but we cannot do that here. The participants were breathing gases in normoxic, hyperoxic, and hypoxic conditions. We used the same voxels that we used to generate 3D micros before, but we generated a dictionary at 3 Tesla. And we have some kind of delineation of the gray and white matter on those data. When the data was acquired, arterial oxygenation was measured by pulse oximetry on the finger of the participants, and a change of the arterial SO2 was found. So we expect to see a change in the SO2 maps that we obtained with MRvF. But when they acquired the data, when Thomas acquired the data, and with the 2D dictionaries that he was generating at that time, he found no statistical change of the SO2 on the subjects. That's why you've never seen this data so far. But with our new proposed dictionary, here are the kind of maps that we obtain in the 3 breathing conditions. We've got very nice BVF maps, nice R maps, nice T2 maps, and on the SO2 part, you can see if your eyes strain that we've got a decrease of the SO2 in the gray matter. I'll come back to that. Only in the gray matter, we do find a statistical increase of the SO2 between the different breathing conditions. And why does it only work in gray matter? Well, because our dictionary is not suited for acquisitions in the white matter. There are some susceptibility effects that we do not take into account here. And so that's why our estimates are so low and not statistically different in the white matter. So I hope I will present that at ISMRM 2023. And to conclude on this study, it is worth simulating dictionaries based on 3D vascular network. I have been saying for a long time that I have to publish this preclinical study. It will happen soon. I intend to refine the data processing that we have to improve the results on human data, because I did not specify that, but we generated this dictionary based on voxels that were conceived to suit the brain of a rat, and it still works with humans. So a bit more work, there is room for improvement here. And we want to include some pathological vascular networks to improve our estimates. Everything that we have from the 3D micro, for the 3D micro dictionary is on healthy tissue, and it's considering the radius distribution is not the same thing in pathological tissue. So we would like to include that in the dictionary using high resolution imaging, as I started to do with the synchrotron here in Grenoble, or by doing dedicated vascular simulations. That concludes this first study, and I'm going to go on with the the last part of this presentation, and show how we intend to find new sequences for MRvF. So we are working here at the very beginning of the pipeline. We want to find a new sequence. So the goal, the thing that we want with fingerprinting is to have different signal shapes when we vary the parameters of the considered tissue. So here, with this sequence from Denmark, the original first MRF sequence, when T2 varies, we have variation of the signals. When T1 varies, we have variation of the signals, and not really the same variations. So this sequence was actually sensible to T1 and T2. It had a good encoding capacity toward those two parameters. And looking at that curve, we can condense a bit the information by computing a point-wise standard deviation for each time point here. And that's what it looks like with the very same sequence for a T1 variation and one fixed T2. This is the standard deviation of the curve, and that gives an idea on how much the curve changes, the shape of the signal changes with a change of one parameter here. Same thing the other way around here. Those are nice curves to look at to assess where the changes are happening and if the sequence is able to encode for both parameters. But when you add more dimension, it gets a bit less tractable, and the information is still not very condensed. So we've been looking at something else, and we found in the literature a method from Sommer, which is actually a Monte-Carlo method. We generate the dictionary for a fingerprint of interest. We extract one signal from this dictionary, which is associated to a parameter vector. We add noise to that signal, and we try to find back in the dictionary the unnoised version of this signal. And as the dictionary in real life will not be perfect if the noise is realistic enough, we will not find the exact unnoised signal, but another one associated with another parameter vector, and then we can compute the error that we made on the parameters by comparing the vectors. We do that as proposed in the paper for 50 signals, and we repeat 2,000 times with different noise each time, and we are able to build this kind of histograms, which inform us that this sequence with the noise that was included here makes, in average, about 7% of error on the VF estimations, and so on the different parameters. We wanted to assess if our implementation of this tool was correct, and so we used data that we have at the lab, and that is the just fits data from the original MRvF implementation. Here is what we obtain using the just fits ratio post over pre-contrast agent injection, which is represented here after the addition of noise. Here are the kind of results that we obtain on this dictionary, and we did the same thing with the concatenation pre over posts that I used in study 1. And you can see that all the errors are lower here. And so we expect to have better estimates using the concatenation rather than relation. That's something that we tried with data that actually come from study 1. So using the concatenation requires one additional dimension in the dictionary. So this experiment is kind of in favor of the concatenation, but it's just an illustration. But overall, on our experiments, we actually found that the concatenation was bringing better estimates. So we believe that this in silico prediction tool actually makes correct predictions. We've been improving the results that we have with the GESFITS data, but the GESFITS sequence is limited. As I said, we really need a contrast agent with that. And it is not a dedicated MRF sequence, and we know that there are many other possibilities. And we are going to try and find to explore those possibilities. One sequence that got our attention is the balanced steady-state free precession sequence type, which we call bSSFP. Just as a reminder, what we want to be sensitive of in the physics of MR is those magnetic field inhomogeneities. And I'm going to make the link and call them the off-resonance frequencies for the normal frequencies that some of you may know. So magnetic field inhomogeneities are directly associated with off-resonance frequencies. And the bSSFP sequence, which is represented here, is well known to be sensitive to magnetic field inhomogeneities. The sequence is called balanced because for all acquisition, the integral of the gradient is null. All the gradients are balanced on both sides of the acquisition. And this sequence is actually, it actually consists, when you acquire a signal, of two parts. A transient state, which you can see here, that evolves towards a steady state, hence the steady state name of the sequence. And why are we interested in this sequence? Well, the steady state part of the signal is well known in the literature to be sensitive to off-resonance changes. It has been used for functional MRI, where you want to detect SO2 changes in the brain that are linked with cerebral activation. Here, the authors show on simulations that they have signal change for an SO2 change that are as high as what you can get with a gradient echo experiment, while retaining the sensitivity and the vessel geometry, basically of the spin echo, and which you can see here on an experiment they made on a volunteer. We do see activation, so we are sensitive to oxygenation changes, and we still have some sensitivity on the size of the vessels, so it seems to fit what we want to do with MR vascular fingerprinting. And a very interesting and exciting part of this work is that the transient states of the bSSFP sequence is mostly overlooked in the literature. It's a part that is quite impossible to mathematically describe, and here the authors tried to get rid of it, but they made a nice illustration on the first line of each panel here. It's the same sequence in different off-resonance conditions, and you can see that the shape of the signal varies a lot. That's exactly what we want to do with MR vascular fingerprinting. In addition, I'd like to stress out the fact that we can play on many parameters in the sequence to gain some sensitivity to off-resonance frequencies. It was done here with this QRF MRF method by applying an RF phase cycling on the second part of the signal here, and you can see some signal variation with global off-resonance frequencies and with intravoxel distributions of resonance frequencies, which is exactly what we want to measure. And the same thing was done here by Wu et al. With the OSI phase cycling, as they call it. And they showed that with different off-resonance frequencies corresponding to SO2 changes, we are able to shift the shape of the signal in time. So that is very promising because, again, it suits the framework of MR fingerprinting. So we tried designing some bSSFP sequences with our Monte-Carlo tool. Here are the results that we obtained. we tried, for the sake of comparison, the just fit sequence that was used before without contrast agents, and we obtained some quite poor results with SO2. Same thing with the QRF sequence that I presented, but when using the OC phase cycling that I presented, or just a bSSFP with random TR and FA trains, everything here is without contrast agent. We have quite low SO2 errors in silico. That's what I presented as a novel at the ISMRM 2021. So we kept working with those two types of sequences, and actually with the help of Thomas Couder, who is in the room today and who is doing his PhD with us, we've been identifying 3 types of sequence using either the OC phase cycling, the random TR and FA trains, or just more standard bSSFP with everything constant. We identified those 3 types of sequences as being of interest. We tried, we simulated dictionaries for about 15 sequences for those 3 types with different FA and TR conditions, and we assessed the error made in the SO2 from Monte-Carlo each time. We identified 2 suitable candidates. We've been refining them, improving the SMR, testing against P1 artifacts. We did quite a lot of work. And we found 1 candidate sequence that should give very low errors on the SO2 estimates. That was presented by Thomas at the 2022 ISMRM conference. So we have this candidate sequence that seems to work in silico. We were very excited. We went to the scanner and we obtained this kind of maps, which, if you remember, the maps I presented before, is of quite poor quality. It's not very usable as it is. So we've been questioning a bit of everything here. Why is it not working? And we noticed that we were never properly matching the signals that we were acquiring. The test match was never really matching the acquisitions, and the machine learning tools that we have were not able to reconstruct with coding maps as well. So we questioned that, and we wondered if our simulations were good enough. And I've been working a lot on vascular representation in my simulations, but I never really considered the scanner representation of my simulations. And if in the scanner, what happens is that we have RF pulses that have a specific shape, and that we hope we have all those imaging gradients that are compensated. What we actually simulate is just that. We consider a hard pulse approximation without any shape, and since the gradients are always compensated, we do not include them in the simulation for the sake of simplicity. And we attributed our mismatch between acquisitions and simulations to that effect, and we started working towards solving that. So not working with amorphous or vascular fingerprinting, just working with regular fingerprinting. We made some tests. Here is the kind of thing that we can, so we've got the acquisition and the match comes directly from raw simulation as we did them before realizing that. Here is what happens when we include the slice profile, maybe a bit better, but not great. And when we also include the inversion efficiency, we are starting to get better matches. So this is still work in progress. We did not reach a point where we solved that problem, but we are working towards that. We are still onwards in the search of the perfect MRvF sequence, but we are quite confident because we have an efficient tool for evaluating in silico our sequences. We are making progress with our simulation tools, and we still have many possibilities to explore with the bSSFP sequence. And in particular, the room that we have for improvement on our simulation tools will be what I'll be working on during my 2-year postdoc here at the gym on the same project. As a general conclusion to these projects, we are able to perform MRF experiments. We have all the electric tools for the simulations. We have a very nice acquisition solution, and we have some reconstruction solutions as well. And we already proposed some improvements for MRvF. I presented two posters and 1 oral at the ISMRM. I intend to publish the preclinical study that I showed in 3D realistic vascular networks. So we already have promising results on human data, and we have what we think are original ideas on the bSSFP sequences. Considering the perspective that we have on the simulation parts, I want to keep improving the vascular network representation with simulated vascular networks. We have to improve the scalar representation in the simulations, and I should really now write an article about MRvF once those problems are solved. We are able to implement sequences from the literature, and that we propose on the physics module, and they seem to be acquired as we want. We believe that a 3D acquisition tool would solve some of the problems that we have with the slice profile and other things. And we want to pursue the preclinical module developments with the help of the Bruker support. And towards the reconstruction, I would like to implement some state-of-the-art dictionary compression and deep learning methods to see how they hold against what we have currently, and maybe solve some issues that we have with the matching. Looking at the big picture, on this project, we have Thomas Couder in the team who is working on automatic sequence optimization. All the work that we did so far was testing sequences by hand, which proved to be very tedious. And Thomas is going to implement some optimization to find directly the perfect sequence. And my postdoc will be part of the MRfuse project led by Thomas. We intend to use the developments from this thesis to replace a 25-minute MRI stroke exam with a single MRF sequence, which we want to keep under 6 minutes for the acquisition, which will evaluate the SO2 among other parameters of interest for acute stroke study. And we will do clinical trials on subacute stroke patients with Dr. Arnaud and Dr. Luc. I'd like to thank you for your patience and your attention. I want to really address a big thank you to Emmanuel and Thomas because they have been a real inspiration and motivation. I want to thank all my colleagues from the platforms without whom I would have been really lost. I want to thank the whole Team 5 for the great times that we have and that we will keep having during these 2 coming years, and maybe more, who knows. And I'd like to thank the jury for being here today, for the patience during this presentation, and for the questions that I'm sure they have. Thank you.